everyone. Welcome back to Learning at 11th Hour. Today we are going to look at an extension of the analysis methods. It's called as the network theorems, and in this video we'll be discussing about Thevenin's theorem. So let's see what the statement of Thevenin's theorem is. It says that a linear active bilateral network can be replaced at any of its terminals by an equivalent voltage source in series with equivalent resistance, wherein the equivalent voltage source is going to be called the Thevenin's voltage source and the equivalent resistance is going to be called as the Thevenin's resistance. So, what does this mean? It means that if I have a circuit that appears in this manner, that is, there is a complete network, a linear active bilateral network which is available, made up of resistors, etc. And that would be connected to a load across these two terminals. Let me call it as A and B. So if I have some load connected over here, so I can replace this linear active bilateral network using a voltage source and a resistor in series with the voltage source, both of which put together are going to represent this linear active bilateral network. And the terminals A and B are going to remain as such, across which the load is going to be there. So let us look at the steps that are involved so that we can obtain the Thevenin's equivalent circuit. So the first step is to identify the output terminals and open circuit the load, that is, remove the load. The second step is to obtain the open circuit voltage. So the load that we just removed across the two terminals, what is the voltage that is going to be there available across those two terminals? That is going to be called as the Thevenin's voltage. The third step is to kill the sources. So if it's a voltage source that is available in the circuit, I'm going to short it. And if there are current sources available, I'll open circuit that particular branch. Then the fourth step is to obtain the RTH, that is the Thevenin's resistance. So to do that, we need to obtain the Thevenin's resistance or the equivalent resistance looking in from the open circuit terminals. The next step is to draw the Thevenin's equivalent circuit, wherein we'll be replacing the entire network with a voltage source, which is VTH, in series with the resistance called the RTH. And then we are going to include the load which we had removed in the first step. So all this put together is the Thevenin's equivalent circuit. And lastly, we can compute the load current. And in order to do that, we can find it out as VTH divided by RTH plus RL is equal to IL. So let's just look at an example and apply these steps one at a time to get a clearer picture as to how we can obtain the Thevenin's equivalent circuit. So say this is the example. For example, here we need to determine the current I in the network and we need to obtain the Thevenin's equivalent circuit. So we can do this using simple mesh analysis, etc. But there are some problems which are much simplified if we go for Thevenin's theorem. So just to simplify and understand the different steps, we've taken up this example. So say I want to determine the current I through the 10 ohms resistor. So in this case, my 10 ohms resistor is going to be the load resistance, and that has been connected across the terminals AB. So the first step is to identify the output terminals, which we just did, right? So this was the terminal A and B, and I have removed the load. The 10 ohms resistance was the load resistance, and I have removed it and open circuited the load. So this is the first step. The second step is to find out VTH, which is going to be equal to VOC. So I need to find out the voltage across the terminals AB, and I'm going to call it as VOC in this manner. So this is going to be the open circuit voltage. Now, in order to do that, let us analyze. So say I call this terminal as XY. Now, if we look at it closely, the voltage across the terminals AB is the same as the voltage across the terminals XY. So I can say that VOC is nothing but VXY. So if I'm able to obtain VXY, I can say that VOC is nothing but VXY, which in turn becomes the Thevenin's voltage source value. Right. So how do I compute Vxy? So we can just simply apply KVL in this loop. So let's assume that this is the direction of drop. So let's mark the voltage drops over here. So this current, suppose, enters this resistor here. It is going to leave here, enter here, leave here, and therefore the drop directions are going to be like this, in this manner. Now, let me apply KVL. So, applying KVL at loop 1, if I call this as my first loop, and there's just one loop. So, I can start by saying, since the direction of 10 volts is opposing the assumed direction, I'll say minus 10 plus 4 into, suppose the current here is I1 that I've assumed in the clockwise direction. So, 4I1 plus 6I1 plus 12 is equal to 0. So that is 10I1 is equal to minus 12 plus 10, which is minus 2. So I1 is equal to minus 2 by 10, which is minus 0.2 amps. So this means the value of I1 is zero point 0.2 amps, but the direction that I have assumed is supposed to be in the anti-clockwise direction because there is a minus sign over here. So that is now taken care of by this minus sign, the direction of I1. Having obtained I1, I need to find out Vxy. So what is Vxy now? So let's look at these drops and find out. Vxy can be written as I1 into 6 ohms plus 12 volts. So what is I1 here? I1 is minus 0.2 into 6 plus 12. So that is 12 minus 1.2, which is 10.8 volts. So therefore, I have obtained my VOC, which is nothing but my Thevenin's voltage, as 10.8 volts. So this is my second step. Moving on to the third step, we need to kill the sources. And we know that if we have voltage sources, then we need to short them. And if we have current sources, we need to open circuit them. So here we have voltage sources in both the cases. If we look at the circuit here, one is 10 volts, the other is 12 volts, both of which are voltage sources. So I'm going to short circuit them. So that is my third step. Even here, we have not included the load yet. Now, the fourth step says that we need to compute RTH across the open terminals. So, this is my open terminals, and I need to compute RTH looking in from the open terminals like this. So, when we look at it, we see that the 4 ohms and the 6 ohms are actually parallel to each other. So, therefore, RTH is nothing but 4 ohms parallel with 6 ohms. So, what is the value of RTH now? Value of RTH is 4 into 6 by 4 plus 6. So, rather we can say 1 by 4 plus 1 by 6, the whole inverse is equal to RTH. So, this boils down to the same thing. So, taking LCM, we have 4 into 6 and 6 plus 4, the whole inverse, which is exactly what we've written here. So, we get 24 divided by 10, which is 2.4 ohms. So, therefore, the value of RTH is now 2.4 ohms. Now we need to draw the Thevenin's equivalent circuit. So that is going to be the Thevenin's resistance, which would be in series with the Thevenin's voltage. And across the terminals A, B, we are going to connect it. So what was VTH which we obtained? It was 10.8 volts. And the RTH that we had obtained was 2.4 ohms. And across the open terminals, we can now reconnect our load, which was 10 ohms, and we know that the current through it was I. Now, if we need to compute this current I, which is nothing but the load current right now, we can do it in this manner: VTH divided by RTH plus RL, where VTH is 10.8 volts, RTH is 2.4, and RL is 10 ohms, which is 10.8 by 12.4 amps, which turns out to be 0.871 amps. So, in this manner, we can, following each step, implement the Thevenin's equivalent circuit and obtain the load current. So that's all with today's video. So today we discussed about the concept of Thevenin's equivalent circuit and how it can be used to obtain the value of load current through any particular resistor by replacing an active linear bilateral network with a voltage source in series with a resistance. So thanks for watching this video. If you have any queries, please don't hesitate to put them in the comments below. And don't forget to subscribe the channel. Thank you.